Hey everyone, thanks so much for signing up for the PCB design workshop. I'm really excited for the semester and I think we have a lot of exciting things to do. Make sure if you haven't already, you join the Piazza for the class so you can forward any questions there so everyone can see it. ECE 7777, which is not a real class, but that's what the Piazza is. So I'll be doing some kind of like Zoom office hours this week to debug issues people have with setting up Altium, which is the only thing that you really should be doing so far. Also, make sure you fill out your availability for a guest lecture next week if you'd like to attend. It should be pretty interesting. Make sure you comment on that Piazza post if you have any topics you'd like covered about PCB design and industry and just general electronics, like scaling up to the scale of industry as opposed to like personal projects you may have done so far. The plan for this week is to go over basic electronics that may come up when you're designing PCBs. Hopefully you've had some exposure to these kinds of things, either through personal projects or classes. If you haven't heard of these concepts or components before, you should look them up. I'm doing basically a cursory overview, not like teaching you how to do all of these things. Later in the week, I'll be posting a soldering video. All the components have been ordered and they're on their way, so hopefully I'll be able to get those to you guys soon, probably out of Philips, hopefully next week. So now I'm going to go over some basic concepts and components that are really relevant to PCB design to hopefully just refresh your memory. Okay, so voltage and current. Hopefully you have been exposed to these concepts before, but I'll just go over them real quick. Voltage is defined as the electric potential difference between 2 points, units of volts, and it's usually relative to ground, which is defined as 0 volts. We also have current, which is the rate of flow of electric charge. We typically have current flowing from like higher voltage to lower voltage. Hopefully you've seen this equation before, V equals IR, so the voltage is equal to the product of the current and the resistance, or more accurately impedance. Very important equation, make sure you are familiar with this. Okay, so what exactly is ground? Ground is a reference voltage. They're digital, analog, chassis, and earth grounds. These are the symbols for them here. So this is earth ground, power ground, and signal ground. Earth ground is literally like metal shoved into the earth, and that's like probably the most true ground because all of the earth is at a single potential. So if you connect grounds back to there, that's going to be all actually the same ground. A chassis ground would be like the metal enclosure around something. So like if you have like an Ethernet jack or like any connector you've seen that has like metal around the edge of it should be connected to ground, and that's like your chassis, the thing surrounding the component. You also have like digital analog signal ground, which are local to your circuit and can be tied to either to the chassis or to the earth, or maybe you don't do that for whatever reason. There's tons of rules and stuff about ground, which we'll get into more when we get into design, but things can be funky with ground, so deciding where exactly to connect ground is a big topic of discussion. One really important thing that is not up for discussion is you have to tie all of your signal grounds together in the same circuit or they can't communicate. Whether you do this from directly just having one big ground plane or from having some kind of like connection point or whatever you do, you have to make sure that they're at least connected in some way so that they can communicate with each other. If you have 2 different microcontrollers on 2 different grounds, they will not be able to talk to each other. So really important. Okay, so AC versus DC power. DC is what you've probably worked with if you've done any kind of beginner electronics. You have like 5 volts to a microcontroller or 24 volts to a motor. That's usually referring to like the DC voltage to something. You would never like power something like that off of AC. AC is alternating current, which is basically like what comes out of your wall socket. Typically, you'll convert this into DC before using it for electronics. Like if you have like a battery or a phone charger, it's going to convert that to DC before it is used for whatever you have. So up next we have our most basic set of components known as RLCs, resistors, capacitors, and inductors, also sometimes called passive components because they can only receive a signal, not amplify, oscillate, or generate a signal. We won't get super technical physicsy about how exactly these components are going to work, just review the critical parameters. So you have impedance is like a super important concept when dealing with these components. Impedance is kind of like resistance, but when you have any kind of signal, so anything that's not perfectly DC. A component will have like a lower or higher impedance depending on the frequency of operation. And the symbol for impedance is the Z. That just means impedance. So first up, we have resistors, these guys. They are not frequency dependent. They will have the same impedance regardless of what frequency is going on with them, for an ideal resistor anyways. These are super useful for things like pull-ups, pull-downs, dissipating energy, and setting voltage level. Next, we have capacitors. So they have a lower impedance with higher frequency relative to this equation here. So the impedance is going to be 1 over the frequency times the capacitance. These are super useful for filtering, coupling, that kind of thing. And up last, we have inductors, these guys here, which will get less, they'll have like a lower impedance for a lower frequency and a higher impedance for a higher frequency. So it's proportional to the frequency by this equation here. These are useful for feedback and power regulation, but we're not really going to get into those a ton because we don't really use them in more basic circuits like we'll be talking about in this intro. So another really common component you're going to see on PCBs is switches and buttons. Their function is to connect or disconnect two or more components. Some major differences you have to look at when you're deciding between switches. Are they normally open or normally closed? So this is a normally open and this is normally closed. Essentially, when it's not being pushed, is it going to connect two things or is it going to not connect two things? A normally open thing would leave it open, would leave it not connected until you push it, which would connect the circuit. And then normally closed, it's the opposite. So it will close the circuit, connect the two components when you push it. Another important thing to look at is how many poles and throws it has. So a pole is the number of circuits that can switch in one operation. So this is single pole, whereas this would be double pole, because there's two circuits here and one circuit here. And then the throw is the number of contact points per pole. So we see this has a single throw versus a double throw. This connects one circuit or disconnects it, and this can connect to two different circuits. This is a double pole single throw because it's only, each pole is only connecting one circuit or disconnecting it, as opposed to switching between two things. Okay, a very primary function of resistors is as pull-ups or pull-downs. When you're reading the state of something like a microcontroller and you have like an input and it's not connected to anything, like if this circuit wasn't here and it was just trying to read an input, it would, and the switch was open, it would be reading nothing. And so you basically just get kind of noise, it's floating, and it'll just return garbage. So whether that input is reading like high or low will just be kind of arbitrary, which is obviously not good if you're dealing with something like a reset where you don't want to just reset randomly depending on the wind. So instead you'll have a big resistor known as a pull-up or a pull-down tied to a known value to set the default state of whatever the input is. So here we have a pull-up resistor, so the default of this will be high, but then when you close the switch, there's lower resistance here, 0 versus something big. 0 wins and it pulls it down. So pull-ups will be default high and the switch will pull it low, and then pull-downs will be default low and the switch will pull it high. So that will depend on whether your input is active high or active low. Active low will react when it's pulled low, and active high will react when it's pulled high. So a reset that is active low, you'll want to have a pull up on, for instance. Diodes. Diodes only let current flow in one direction, ideally for a given set of parameters. If you have a crazy high voltage, like eventually you're going to break that diode, and it's not going to apply. You need to have the high side and the low side connected to let current flow. So the most common thing you'll see, most common diode you'll see in a circuit is usually, or basic circuits at least, will be an LED, a light emitting diode. They only emit light when the voltage is correct, the voltage is high enough in one direction. It will only let current flow in one direction from the anode to the cathode. And this is the circuit symbol that you'll see for that. It's really important to hook these up in the right direction. If you like solder them backwards, they will not work. That's like the whole point. Transistors. Transistors are like a super critical tool used in almost every circuit ever, but they are also very complicated and there's a lot to them, and I can't really cover the entire range of use cases. If you want to learn more about these, there are just a ton of classes you can take. ECE 3150, Analog IC, RFIC, VLSI, Computer Architecture. You're just gonna talk so much about transistors. So if you want to learn more about them, you have many opportunities to do so at Cornell. Digitally, they can be used like a switch, and analogically, they can amplify signals like an op-amp, if you've worked with those before. ICs, which we'll go over in just a second, are made up of thousands to millions to billions of these. Sometimes we'll just use discrete transistors and things like high power switching cases or reverse polarity protection just as a switch or whatever. And these are like a BJT versus a MOSFET, which are two popular kinds of transistors that you'll see the circuit symbols for when working with the schematic. Okay, DACs and ADCs are like opposite tools used to switch between digital and analog signals. So digital signals have a switch between like discrete values, whereas an analog signal is like a smooth, continuous thing. So example here, like this would be a digital signal of just bits, and this would be an analog signal of continuous curve. So ADCs convert analog to digital, which is useful if you want a computer to measure something in an intermediate voltage. Say if you're measuring like light intensity or sound or something like that, and it wasn't exactly a binary value, you'd want to convert it to a digital value to be read by the computer to understand it. And whereas a DAC is the opposite, a digital to analog converter. A computer can only generate like binary values, but if you want, for example, audio, it's going to sound like complete garbage if you just have bits. So you're going to want to convert that into a smooth signal to output into a nicer sound, for example. So a potentiometer is a tool that may be used as an input to an ADC. It sets an intermediate voltage by sweeping across a range of resistance values. These are useful for like setting values for user input or monitoring the location of a spinning part such as a motor. They'll give you an intermediate value between whatever range of resistance is available for that potentiometer, usually like 10K. ICs. ICs stand for an integrated circuit, which is the opposite of a discrete component that we've been talking about so far. There are millions of different types of ICs for specific purposes, ranging from big complicated tasks like a whole microcontroller to something more simple like a linear regulator, op-amp, something measuring a specific value, a sensor. They come in all different shapes and sizes, seen here, but they're often like a little black plastic thing with little legs or balls in the case of a ball grid array. So you'll use different packages depending on what your use case is. Different viabilities depending on the application. For instance, like a BGA stands for a ball grid array. Super useful if you want like a really compact circuit. You know, size is a really big problem for you, but it's going to be nearly impossible for you to hand solder. Like you're not going to be able to do this with a soldering iron because these are all internal pins. So forget it if you're trying to hand solder it. Whereas a dip package is going to be super easy to hand solder. It's a through hole, goes right through the circuit, super easy to solder. Really great for prototyping and that kind of thing. But if you're doing a product where space is a concern, not very useful. It takes up a ton of space and is like unnecessary for that. So we'll be going over a few different kinds of these packages in the future of like useful things to use and why. A microcontroller is a common tool on PCBs because they're essentially like small, fast, cheap computers that can be used for like programming a very specific task. It can have like a CPU, memory, inputs, outputs, but it's really very simple. It's not crazy complicated, but you can have a more complicated microcontroller too. They vary hugely in their uses from like 8-bit tiny ATtinies to huge like 64-bit STM microcontrollers. They're different from a full computer because they're real time, so they don't have like an operating system that they're running, like Windows or Linux or Mac OS. They're not running an operating system to go through before making decisions, so they're a lot faster and really good for like specific purposes. Again, if you want to learn more about microcontrollers, there are a few courses on them in the ECE department, specifically going into a lot more about microcontrollers and their uses and how to program them, that kind of thing. The microcontroller that's used on an Arduino Uno is the Atmega 328P. It's the part number for it. This is like a smaller Atmega, which we'll be using for the first project in this course because it's very simple, easy to use, well documented, and you can program it with an Arduino IDE if you don't like programming like me. So next we have crystals, clocks, and oscillators. These are different components, but they're all essentially like used for the same thing, which is keeping time in circuitry. And some have internal circuitry to keep time very precisely, and some require external circuitry to stay consistent. Accuracy is super important for a lot of real-time systems to keep track of computing cycles and to operate in a timely manner. Some MCUs and ICs will have built-in oscillators, and others will require external circuitry. So for instance, the IC we're using, the MCU we're using, the Atmega 328P, it has an internal oscillator, but it's only accurate to around 10%, which is kind of garbage if you want anything like good. The application we're using it for doesn't really require something more precise than that, but we can often apply an external oscillator to have like more accurate timing within the circuit. Connectors and headers are how you're going to interface your board with the outside world. There are millions of different connectors out there, and the choice may be more involved than you may think. For instance, in automotive and aerospace applications, connectors are like a really serious research field because you need it to be really good for whatever application you're using it for. First and foremost, obviously, you want like to have the right number of pins, but there's a ton of other things to consider when you're picking your connectors, like the current capacity for each pin on the connector. So it needs to be rated high enough to handle your operation. You don't want to connect a huge motor to a tiny current limited header. It would burn up and could possibly cause a short. I've like melted headers before because they're just plastic a lot of the times. You might also want to consider the life cycle. So are you gonna like continuously plug and unplug this thing, or are you just gonna like leave it there and plug it in once and just leave it there, and that's how you're connecting it to a circuit? Only unplug it if you need to test something. Your life cycle matters, whether it's like 10 cycles or like 10,000 cycles. Some connectors have lock-in capability, so you need to have like push in a tab or something to unplug it, and that's really great if you don't want it to like accidentally come unconnected if it's like being pulled on for some kind of strain in the circuit. Now, some are also directional or keyed, which means you can only plug it in one direction. This is really huge for power cables because if you plug in a battery backwards, you could damage the board and the battery and possibly cause a fire. I've also done that before. So really important categories of connectors. These are XT60s, really high current, directional, as you can see. Really great for like batteries and giant motors and that kind of thing. These are much smaller, like JST headers, good for like sensors, low current things. And this is just like a typical like header that you'd have for like a programming cable or something that will be like removed during typical usage. Okay, so communication protocols. These are for like if you need to communicate between like a sensor and microcontroller, or a microcontroller and another microcontroller, things like that. If you need to send data over a line. The protocol is defined by how bits are sent to one another, in what order, at what rate, etc. You can use many things to define the protocol. Is it synchronous or asynchronous? Like your classes on Zoom this semester, the degree of impedance control, whether it is directly between two components or on a bus. So this is like a bus example. SPI can have a bus, so you can have like multiple things on one thing, whereas serial, TX and RX, you can only have one thing connected to it at a time. Is it wired or wireless? So like Wi-Fi, Bluetooth, that kind of thing. I stole this lovely graph from Kirsten's 3400 notes, because it's a very good comparison of some common wired protocols that you would generally use on a PCB. So we have UR at SPI and I squared C, I2C or I squared C. People say it different ways. Some people also call this SPI instead of SPI, whatever. So they have different maximum speeds. But for instance, so like SPI is like faster, but it's gonna use a lot more wires. It's gonna use 4 wires as opposed to just 2 wires. So it's a trade-off between space and speed on your circuit. The concept of master and slave in this context refers to which components control the line, which are the masters, and which ones take commands and have to request access to send back info to the master. For instance, like a sensor reporting to a computer, the sensor would be the slave and the computer would be the master. So that's what that means here. Yeah, so this is just some common ones that you would use. And the synchronous versus asynchronous is like whether it's like on a clock is when you can request things and when you can send them, that kind of thing. So finally, I just wanted to do a quick review of filters. Hopefully you have done this at least briefly, like a physics class, if not thoroughly in a circuits class already. So I cannot like just go over all of this right now, but The general concept is using like passive components to control what kind of signals will get through a filter and which ones will be rejected. So if you have like a low pass filter, you will let through the pass band, which is in the low frequency in this case, and then you will reject everything in the high frequency, and the high pass is the opposite. So you reject low frequency, including just DC, so like 0 hertz, and you'll let through high frequency signals. And there's also band pass and band reject, as you can see here, just letting through a certain range or just rejecting a certain range. This is useful if you want to let, like, if you have a communication, like a wireless communication, and you want to just like only see that signal, or if you want to reject like a common like noise, like you might have a notch filter at 60 hertz, for instance, because that's what like power is, and that can be kind of like noisy on a circuit sometimes if you don't have a very good converter for DC. And the values, like what exact frequency this is going to switch at and what it's going to reject and what it's going to let through, is determined by the values of your passive components in your RLC filter. So like what resistor and capacitor do you use? Okay, so that's like a very cursory overview of components and concept used in PCB design. Really do look into anything that you weren't familiar with. All of these things are going to be very important when you're designing PCBs. We'll be using these components and concepts in our circuits this semester, which will hopefully give you like a more intimate understanding of their usefulness. If you have any questions about any of these things, post on Piazza, come to Zoom office hours, email me, whatever works. But you really should have a general understanding of these concepts before we start. All right, thank you. See you later.